I'm showing here the compound pendulum that you'll be using in the lab. The pendulum is made of aluminum, shown here, rigidly attached to the shaft that is supported by these two bearings. And it's coupled here to a potentiometer, right? It's actually sitting on the back of this support here. And there's some data for this pendulum that gives you the geometry and also the aluminum material properties, so that as we ask for in the pre-lab, you can determine the moment of inertia about the pivot point, also find the length to the CG, etc. Okay. That potentiometer will be set up for you in the lab. There's 3 connections on a potentiometer like this, and you usually configure it as a voltage divider, if you like to think about it that way. I mean, both of these resistors are changing. This is the total resistance. So let's say that you say, oh, this is a 10 kilo ohm potentiometer, right? The resistance is always changing of R1 and R2, because this swipe here is always moving. Think of this here as where the shaft is connected and it's rotating. So what you're basically doing is right, you're creating this voltage divider. This is the voltage out that's going to basically go to your analog 0 input on your Arduino, and you could compute this if you wanted, but the best way to do this is, of course, just set up this potentiometer. You want to sometimes adjust the potentiometer so that when, like in this case, let's say the swipe is going to be down here if it's connected, so that it gives you, R1 equal to R2, so that the voltage is right in the middle. And by the way, sometimes, what you do is you connect these two, right, to, like let's say you have plus 5 volts, and here this might be the ground, or sometimes you might have minus 5 plus 5, and then this, when it's centered, the output when it's centered would be 0. Since Arduino, it's with a unipolar 5 volt output if we power it with the Arduino. And by the way, again, you would want to make sure that you don't draw a whole lot of current from this. Arduino can only, but it can power a simple potentiometer here. By the way, we purposely choose, I think this is a 10k ohm potentiometer, so it doesn't draw a whole lot of current. You don't want to draw a whole lot of current from the Arduino. You could also power this with an external power supply, where you possibly could put minus 5 plus 5 if you wanted the output to be between, minus 5 and plus 5. So it'd be like negative, could be negative angle, positive, positive angle, and negative angle about the 0, say. But we're going to be going from 0 to 5 volts, so if you center it, it should be about 2.5 volts approximately, right? Think of this as, right, your sensor and your signal conditioning, and that's part of the whole idea of how you build a sensor. Remember, resistors are really simple. We take advantage of the fact that wire has some resistivity. The length determines the resistance, so does the area and the resistivity, but it's the length that's changing here, how much you have on each side of that swipe, and that's how you basically make a sensor. A lot of sensors are built this way, so again, just wanted to give you that little background. The calibration is very useful and essential. What you'd like to do then is, you're going to give it a known angle, and we're going to give you a way for you to position the potentiometer, say, at some angle, and then you can measure that angle, from the vertical, and then use that as your input. And then you can also measure the output on Arduino. You can monitor that with a serial monitor step by step, right? Go from negative to positive angle, and you basically build a table, and that allows you to build a calibration curve. And so today we'll walk you through all that. You think about how you're going to do that. How many points you want. Sometimes, as long as you'd want to get it close to 0, something out here, something out here, so minimum 3, but it's nice to get more, just so you can see if you've got maybe a linear trend there between voltage and angle. I'm drawing it this way about 0, but in reality, of course, it's going to be 0 to 5 volts, and so the middle is going to be somewhere around here. So this is going to be 0 theta. This is going to be like say minus 90 degrees, plus 90 degrees, right? So think about all of that before you go to lab, so you're ready to kind of hit the ground running. We always check linearity. Now, why do we like linear sensor models? You want to, the output related to the voltage, say, by some constant. And the only reason we like that is because, so if you look at the voltage and it transforms linearly in your mind. So if you see a certain trend, if you see, the pendulum moving this way, then if that's the voltage, then, and if this is supposed to represent theta, then the angle's varying that way. If this relationship was not linear, then you couldn't look at just the voltage. And so that's a very traditional kind of idea. Nowadays, since we have computers that can compute things, we can plot things very easily, through some kind of nonlinear function. If you did find out that, hey, when I went through and calibrated my potentiometer, it actually had this really strange, trend, you just build a function approximation for that and use that function all the time to give you, what is theta when I have an when I have a measured voltage. Keep in mind, I was drawing it this way before. Voltage, I was measuring that input theta, but when you use it, actually, you kind of use it this way. What is the angle when I have a certain measured voltage? That's the calibration constant that you want, right? Sometimes we actually won't do this, but in later labs, once we have the data in the computer and this shows the trend that you typically see on these potentiometers, the kind of trends that you see, we'll study that more in other labs. Kind of what does that reveal? There's a really neat program called, that'll pick up the peaks and so on. We'll do that in another lab, not in this coming lab, but just something to think about. Once you get, the acquired data, then you can do a lot of stuff with it. Again, the pot sensor potentiometer is pretty well behaved. Gives a nice continuously varying or analog output voltage. We're practicing using analog measurement on Arduino. That's what this is all about. We could use other kinds of sensor like digital encoders and so on to measure angles. I just wanted to have at least one lab where you practice measuring voltage. Be careful with some sensors, like sometimes they don't give a good resolution. You might not get a good discrimination between different levels of a certain quantity that you're trying to measure. I mentioned an end-to-end calibration sometimes, and that's like, so we're going to connect everything up to the Arduino, and then you calibrate with the Arduino, rather than having, someone says, here's a sensor that has this calibration constant, and then you have to connect it to your own measurement setup. Sometimes the differences in impedances and so on, you have different electrical loading. It can cause small errors. It's not a big deal, but doing an end-to-end calibration is always a very good way. In other words, you calibrate with the Arduino, you collect data with the Arduino, and everything is all matched up nicely. Okay, so that's sometimes what we call an end-to-end calibration. Again, continue to practice Python. We're going to now be combining Python with Arduino, and I'll talk about that in a different slide. I have a couple of slides here that finish with using linear regression. Pretty straightforward with Python. We can always use available routines for doing linear regression. I include a linear regression routine here that I wrote, but use, and I think I included that on the Canvas page, but the TA will show you their preferred way for doing linear regression.